Well, good morning. Welcome to everyone joining this meeting of the Carcinogen Identification Committee. The meeting is being held in person and virtually. My name is Dr. Dave Edwards. I am Chief Deputy Director and Acting Director of the Office of Environmental Health Hazard Assessment, or OEHA. Lauren Zeiss retired as the OEHA Director in June of this year. OEHA is a department within the California Environmental Protection Agency and is the lead state agency for the assessment of health risks posed by environmental contaminants. As we get started, just a couple of housekeeping items for those attending in the room here in Sacramento. The emergency exits are through the double doors directly in the back where you entered the room, and at the front of the room to the left and right under the lighted exit signs. And you can access the restrooms by going out the back double doors and turning left, walking to the end of the hall. We have two newly appointed members of the committee, and I'll be introducing and swearing them in shortly. Our main agenda item today is for the consideration of vinyl acetate for listing as a carcinogen under Proposition 65. After the vinyl acetate agenda item, the committee will take up a consent item on the Section 27,000 list of chemicals for which testing has been required but has been inadequate. This is different from the Proposition 65 list. For the third and final agenda item, staff will present updates on various Proposition 65 regulatory and other activities. We will take a 45-minute break for lunch around noon and take a short 15-minute break sometime in the afternoon. This meeting is being recorded and transcribed. The transcript will be posted on OEHA's website. During this meeting, there will be an opportunity to provide oral public comment on the vinyl acetate item. Individuals who are in person and wish to make an oral comment at today's meeting are asked to fill out a blue comment card and give them to OEHA staff. If you want to raise your hand, that'd be great. Thank you. Blue comment cards are located in the back of the room. When called by the chair, please approach the microphone. Please state your name, affiliation, and provide your comment. Those who are joining us virtually and wish to make an oral comment at today's meeting are asked to join the Zoom webinar. Information on how to join via Zoom is shown on the slide. Go to the URL on the slide and register for today's Zoom webinar. You will receive a link to join the webinar at the end of the registration process, and if you provided a working email address, you will also receive an email with a link to join the webinar. Zoom users can also access closed captioning by clicking the CC button on the bottom panel of the screen. Those of you watching by CaliPA webcast will be able to watch the meeting, but you need to join the meeting by Zoom to speak. When requested by the chair, individuals on Zoom may queue to provide oral comment by using the raise hand function. When your name is called during the opportunity for public comment, you will be prompted to unmute yourself. Please unmute yourself, state your name and affiliation, and provide your comment. If you would like to present slides during your public comment and have not already sent them, please email them now to p65public.comments@oeha.ca.gov. Public comment will be limited to 5 minutes per commenter. Great. So now I'd like to turn into the swearing in and introducing of the new CIC members. Starting first with Dr. Ludmil Alexandrov. He is an associate professor in the Department of Cellular and Molecular Medicine and the Department of Bioengineering at the University of California, San Diego. Dr. Alexandrov received both his PhD and Master of Philosophy in Computational Biology from the University of Cambridge in the UK and his Bachelor of Science in Computer Science from Newmont University in Utah. He did his postdoctoral training at Los Alamos National Laboratory in Theoretical Biology and Biophysics. Dr. Alexandrov has done extensive work developing knowledge on the ways factors, including environmental and industrial chemicals, cause cancer in humans, utilizing the latest tools in doing so. His research is focused on developing novel machine learning approaches and in leveraging these approaches to elucidate the basic molecular mechanisms underlying cancer development and cancer progression. Welcome to the committee, Dr. Alexandrov. Next, Dr. Dean Felsher, who is attending remotely. Dr. Felsher is a professor of medicine, oncology, and of pathology at Stanford University School of Medicine. He serves as director or co-director of the Translational Research and Applied Medicine Center and several research and training programs. Dr. Felsher received his BA from the University of Chicago and his MD PhD from UCLA. Dr. Felsher is interested in how oncogenes initiate and maintain cancer. Dr. Felsher, along with his laboratory, is studying the basic mechanisms of oncogene addition, during which cancer can be briefly reversed by shutting down oncogenes. He is developing novel therapeutics using small molecules, nanoparticles, and proteins peptides that can be used to target oncogenes and/or restore the immune response against cancer, as well as new diagnostic and imaging methods such as PET, mass spectrometry, and nanoproteomics. Welcome to the committee, Dr. Felsher. All right, I will now lead them in the oath of office. New members, you'll be asked to say "I" and then state your name. You may choose to solemnly swear or solemnly affirm the oath. So I guess if both of you could just raise your right hand. All right, it's going to be fun. All right, so we'll just for the first line, we'll go ahead and have Dr. Alexandrov say his name first, and then Dean will go with you. All right, so I.
I, Ludmila Alexandrov.
Dean.
I, Dean Felsher.
All right, now we're going to try to do the rest in tandem. Do solemnly swear.
Do solemnly swear.
Do solemnly swear.
That I will support and defend the Constitution of the United States.
That I'll support and defend the Constitution of the United States.
That I'll support and defend the Constitution of the United States.
And the Constitution of the State of California against all enemies, foreign and domestic.
And the Constitution of the State of California against all enemies, foreign and domestic.
And the Constitution of California against all domestic enemies, international and domestic.
That I will bear true faith and allegiance to the Constitution of the United States and the Constitution of the State of California.
That I'll bear true faith and allegiance to the Constitution of the United States and the Constitution of the State of California.
And I'll bear true allegiance to the Constitution of the United States and the Constitution of California.
That I will take this obligation freely without any mental reservation or purpose of evasion.
That I'll take this. That I'll take this. That I'll take obligation. You know, let me just. That I'll take this obligation freely without any mental reservations or purpose of evasion.
That I'll take this obligation freely without any reservations or
purpose of evasion.
Or purpose of evasions.
And that I will well and faithfully discharge the duties upon which I'm about to enter.
And that I will well and faithfully discharge the duties upon which I'm about to enter.
And I will well and faithfully discharge the duties about which I'm about to enter.
All right, congratulations. We are honored to welcome you to the CIC committee. Your deep understanding of carcinogens and contributions in your fields will add to this esteemed body, which makes the state of California a leader in identifying carcinogens and protecting people in the state from them. All right, so now I will introduce the CIC members, the rest of the committee. So as I introduce you, please state your name and affiliation. Jason?
Good morning, everyone. Jason Bush, Associate Dean, College of Science and Mathematics, Professor of Cancer Biology, California State University, Fresno, and Adjunct Faculty, UCSF, Fresno.
Thanks. Catherine?
Yeah, Catherine Crespi, UCLA School of Public Health and Johnson Comprehensive Cancer Center. I'm a professor of biostatistics.
David?
Dave Eastman. I'm a professor emeritus from the University of California, Riverside.
Joe?
Hi, my name is Joe Landolf, and I'm Associate Professor of Molecular Microbiology and Immunology, Pathology and Molecular Pharmacology and Toxicology, and a member of the Cancer Center of the University of California, University of Southern California in Los Angeles, California.
Thank you. Dana?
Good morning, Dana Loomis, the chair of the, it's on. At least the green light's on. If this works better. Yeah, Dana Loomis, recently retired from the Plymouth County Public Health Agency and the Desert Research Institute.
Tom?
Hi, Thomas McDonald. I'm Associate Research Director. I serve as the lead of product safety for research and development of all of the Clorox company.
Mariana?
Good morning, everyone. I'm Mariana Stern. I'm a professor of population and public health sciences at the University of Southern California and the Keck School of Medicine, and associate director of population science at the USC Norris Comprehensive Cancer Center.
Sophia?
Good morning. My name is Sophia Wong. I'm a professor in the Beckman Research Institute at the City of Hope and a member of the City of Hope Comprehensive Cancer Center in Duarte, California.
All right. And now Ahmed, who's attending remotely.
Good morning. I'm Ahmad Besaratinio. I'm a professor at the Department of Population and Public Health Sciences at the University of Southern California in Los Angeles.
So welcome, everyone. Great to see the majority of us here in person today. We do appreciate you taking the time to provide your advice and judgment at this meeting. All right, next I'd like to introduce OWIHA staff. For those in the room, I invite them to raise their hand. And for those joining via Zoom webinar, I invite them to turn on their cameras. So we'll start with Dr. Kanan Krishnan. He's the Acting Director for Scientific Programs. And if I ever need to step out, Dr. Krishnan will take my place. Not expecting that today. And from the Reproductive and Cancer Hazard Assessments branch, we have Martha Sandy, the branch chief, Dr. Meng Sun. She's currently branch chief of the Air and Site Assessment and Climate Indicators branch. And right, I guess leading up to December, before that, she was the section chief of the Cancer Toxicology and Epidemiology section. And then we have staff of the Cancer Toxicology and Epidemiology section that are joining us today. Doctors Isabel Alvarado, Vanessa Chung, Sarah Elmore, Ila Guha, Kate Lee, Gwendolyn Osborne, Karen Ricker, Huang Sai. We also have members from our Office of External and Legislative Affairs, our Proposition 65 implementation team. We have Tina Cox, who's a senior environmental scientist, section chief of the Proposition 65 implementation program. Tina's also acting for Amy Gilson, OWIHA's deputy director for external and legislative affairs. Yana Baghepi, an environmental scientist in the Proposition 65 implementation program, and Julia Doloff, a senior environmental scientist and our new Proposition 65 ombudsperson. And then from OWIHA Legal, we have Corey Friedman, a senior staff counsel. Great, so I think that's all the introductions. So now I'll ask Corey Friedman for some introductory remarks about Bagley Keene and other legal issues related to participation in today's virtual meeting. Courtney.
How's that? Good morning. No? Okay. Better? Okay. Good morning, everyone. Nice to see you. For those I haven't met before, nice to meet you. I'm Corey Friedman, as Dave said. I have just a few things to remind you of before we get started with the substance of the meeting. Feel free to ask me questions at any time during the meeting. I'll be here the whole time. If for any reason I have to step out, my colleague Christy Morioka is here as well. So there will be a lawyer present the whole meeting. First, a quick reminder that Bagley-Keene Open Meetings Act applies to this meeting, the basic idea of which is that the public's business should be done in public. So for the committee members, please remember that all discussions and deliberations about agenda items need to be conducted during the open meeting. So not during breaks, lunch, or with individual members on or offline, including phone, email, chat, text, any other method. For those who are participating remotely, you need to appear on camera during the meeting unless you have a loss of internet connectivity or something else makes it technologically impracticable for you to keep your video on. So if something like that does happen, please announce the reason before you turn off your video. Remote committee members also need to disclose if there is anyone 18 or older present in the room with you and your relationship to those persons. So I will pause now to see if anyone needs to make that disclosure. Seeing no nodding heads, so I will continue. Next, all the experts serving on this committee have participated in mandatory ethics training and have disclosed any actual or potential conflicts of interest, including any relevant ex parte communications about the subject matter. Finally, I'd like to remind you that the listing criteria that's been adopted by this committee is in your binders under criteria. These criteria were adopted by the committee to help you make decisions about potential listing of chemicals. Your decision should be based on those criteria, not on the consideration of any possible future impacts of a listing, such as whether or not warnings would be required for any particular exposure. In other words, the members of this committee were appointed by the governor because of your scientific expertise and are considered the state's qualified experts on the carcinogenicity of chemicals, but there is no need to go outside that charge. I think we have a slide here. This is just as a reminder, there are 4 separate and independent listing mechanisms, i.e. ways in which a chemical can be listed under Proposition 65. In addition to the state's qualified experts method, whereby the CIC or the DART IC, which is the equivalent to the CIC, but for reproductive toxicants. In addition to that method of listing, there are the other ones on that slide. It can be listed as formally required by an authoritative body or under the California Labor Code. However, the criteria for those other methods are not relevant to your determination today, so you should not consider them. It does not matter whether or not the requirements for the other methods of listing have been met. During the course of the meeting, if you feel like you have insufficient information or you need time to think about the issues in front of the committee, there's no requirement that you make a decision today. You can defer your decision to another meeting and give staff suggestions on the information you need. We would be happy to get that information and present it at a future meeting. But of course, staff are here today, so if there's any questions that you can ask that can be answered today, everyone will make the utmost effort to do so. Your charge today is to determine, or actually your charge at every meeting, is to determine whether the chemicals presented are clearly shown through scientifically valid testing according to generally accepted principles to cause cancer. The standard is a scientific judgment call. It's not a legal standard of proof. This committee can decide to list a chemical based exclusively on animal evidence. The chemical need not have been shown to be a carcinogen in human studies. As stated in the guidance criteria adopted by this committee, the CIC will normally identify a chemical for listing if the weight of scientific evidence clearly shows either that a certain chemical causes invasive cancer in humans or that it causes invasive cancer in animals unless the mechanism of action has been shown not to be relevant in humans. In addition, whether or not there are human exposures to the chemical, or whether or not current human exposures are sufficiently high enough to cause cancer, is not relevant to the listing decision. The CIC only considers hazard. Dose response assessment occurs at a later stage outside the purview of this particular meeting. Whenever OEHA proposes a no significant risk level for a listed chemical, the members of this committee are given the opportunity to comment. As I've said before, feel free to ask clarifying questions of the OEHA staff during the meeting, and if we don't know the answer to your question right away, we'll try to find it as fast as we can and report it back to you. Also, if after this meeting, at any point, you have any questions about Bagley-Keene, feel free to get in touch with me and I'm happy to answer them. And that is it for me for now, so I will turn it back over to Dave Edwards.
Thanks, Corey. All right, well, now I'll turn it over to Dr. Loomis, the committee chair for the meeting today. Dana.
Thank you, Dave. I'd like to begin by greeting all of the continuing members of the committee. It's great to see all of you again, and also express my pleasure in meeting the new members joining us today for the first time. Committee staff for their work to get us prepared for this meeting, and members of the public who've chosen to attend today, whether in person or online. So with that said, we'll go ahead with the first agenda item, which is consideration of vinyl acetate as known to the state to cause cancer. We'll begin with a presentation by the staff. I think Dr. Sun will kick that off for us.
Thank you, Dr. Loomis, and good morning, everyone. Welcome, CIC members. I'm speaking to you today on behalf of all staff scientists of the Cancer Toxicology and Epidemiology section. Let me first provide some background on the process by which vinyl acetate was brought to you today. Vinyl acetate was brought to the CIC for consultation and prioritization in 2016, and the CIC recommended that vinyl acetate be placed in the medium priority group for future listing consideration. OEHA selected vinyl acetate for consideration for listing, and in August 2023, OEHA solicited from the public information relevant to the assessment of evidence on its carcinogenicity. Information received at that time was reviewed and considered by OEHA in the course of preparing the October 2024 Hazard Identification Document, or HID. This document, as well as the references cited and the public comments received on the document, have all been provided to you for your consideration. The HID and the presentation you will be hearing and seeing today are the work products of all staff scientists of the section, and not just those who are speaking to you today. OEHA scientists are at the meeting and will be able to answer any clarifying questions. So now I will turn it over to Dr. Osborne to start the presentation.
Can you hear me? Okay. Good morning. Today we're going to present a summary of the evidence on the carcinogenicity of vinyl acetate. Oh, there we go. Okay. All right, I'm going to start with an introduction, then present the carcinogenicity data, starting with the epidemiological studies. Then Dr. Lee will present the animal studies. Dr. Ricker will present the pharmacokinetics and metabolism of vinyl acetate. And Dr. Chang will present data related to the key characteristics of carcinogens and similarities between vinyl acetate and its key metabolite, acetaldehyde.
Okay. Vinyl acetate is a monocarboxylic unsaturated aliphatic ester as shown on the top of the slide and is volatile and soluble in water and organic solvents. It is a high production volume man-made chemical used in many applications. Vinyl acetate is mainly used as a monomer to produce polymers and copolymers, such as polyvinyl acetate and ethylene vinyl acetate copolymers. There are many industrial or commercial applications of these vinyl acetate-based polymers, such as adhesives, paints, and coatings. In addition, vinyl acetate is approved by the FDA as a food additive as vinyl acetate monomer and vinyl acetate-based polymers. Vinyl acetate has been detected in the environment and various consumer products due to its wide use. Occupational exposure is likely via inhalation or dermal contact. The general population may be exposed to low levels of vinyl acetate via inhalation of contaminated air, ingestion of contaminated water or food, or dermal contact with products containing residual vinyl acetate monomer. However, no biomonitoring data were available. Vinyl acetate has been reviewed by 2 other health agencies. IARC, or the International Agency for Research on Cancer, is one of the authoritative bodies for Proposition 65, and they classified vinyl acetate as a Group 2B carcinogen in 1995, with inadequate evidence in humans and limited evidence in experimental animals. In making the evaluation, the working group took into account these 3 considerations. Vinyl acetate is rapidly transformed into acetaldehyde in the body. Second, there's sufficient animal evidence for the carcinogenicity of acetaldehyde, which is listed as a carcinogen under Proposition 65. Both vinyl acetate and acetaldehyde induce nasal cancer in rats. And third, both vinyl acetate and acetaldehyde are genotoxic. Note that vinyl acetate was not listed by Proposition 65 via the labor code mechanism because this mechanism requires a classification of Group 1, 2A, or 2B with sufficient evidence in humans or animals, which vinyl acetate did not have at the time of IARC's review in 1995. Additional studies have since been published, which will be described later in the presentation. In 2011, the European Chemicals Agency classified vinyl acetate as a Category 2 carcinogen suspected of causing cancer. The CIC placed vinyl acetate in the medium priority group for future listing consideration when we prioritized chemicals in 2016. This is why we prepared the hazard identification document and are presenting it for your evaluation today. Now we'll go through the evidence relating to the carcinogenicity of vinyl acetate, starting with the epidemiological studies. Oh, are you clicking? Okay. Okay. The literature search identified less than 10 relevant epidemiologic studies reporting on vinyl acetate exposure and cancer. There was only one study population per cancer outcome with some overlapping publications. Each included study was evaluated thoroughly for potential biases using general guidance from the NTP Report on Carcinogens Handbook and the IARC Monographs Program Preamble. All studies except one were conducted in workers who were co-exposed to many known and suspected carcinogens. Some examples of these are shown on the slide, such as vinyl chloride, 1,3-butadiene, and styrene. Overall, there were some elevated risk estimates, but these studies all had issues with quality, and chance, bias, and confounding could not be ruled out. One study was not in an occupational setting, which we'll now take a closer look at, and that study was Heck et al. This was a study of air toxics conducted within the multi-ethnic cohort. The analysis included more than 48,000 women in the greater Los Angeles area. This map shows the exposure concentrations of vinyl acetate in Los Angeles. Residential addresses were geocoded according to the year 2000 census tracts and linked to National Air Toxics Assessment, an ongoing review published by the US EPA. Several US studies of time activity patterns provide evidence that home measurements of air toxics are a good proxy for overall exposure to these chemicals. The participants were then followed up for incident invasive breast cancer between 2003 and 2013 through linkage to the California Cancer Registry. These are the vinyl acetate results for the Heck et al. Study. with the risk estimate of 1 shown by the dotted vertical line on the left. In all women combined, a more than 5-fold increased breast cancer risk was reported with 1 interquartile range increase in ambient residential vinyl acetate levels in the overall analysis after adjustment for several potential confounders. The authors were able to conduct several sensitivity analyses since the large sample size provided adequate statistical power. The risk estimates remain consistently elevated in these sensitivity analyses, including in non-smokers, stratification by hormonal receptor cancer subtype, by race ethnicity, and in women who never moved from their residence throughout the study period. The highest adjusted risk estimates were observed in women with hormone receptor negative tumors and in African American women. Vinyl acetate levels varied across neighborhoods and between racial ethnic groups. The authors noted that African American participants lived primarily within the area bordered by several freeways with high levels of traffic-related and specific agents compared to white participants. There were several strengths of this study, including a large sample size, prospective cohort, multi-ethnic population, detailed questionnaire that collected data on multiple covariates, and detailed residential histories available for residents who lived in California during the study period. There were also a few limitations. Precision may have been hampered by using air pollution models that give exposure estimates at the census tract level, not for individuals. A non-exhaustive list of chemicals was assessed, some of which could be correlated with other unmeasured chemical exposures. And finally, important earlier life exposures could be missing since the exposures were estimated only during the study period. That concludes the presentation of the epidemiologic studies, and now Dr. Lee will present the evidence in animals.
Can you hear me? Dr. Osborne. Thank you, Dr. Osborne. Now I will present vinyl acetate carcinogenesis studies in animals. A total of 24 long-term studies has been conducted in rats and mice by laboratories across the US, Japan, and Europe. In rats, there were 16 studies conducted in 5 strains, with 2 using the inhalation route and 14 via drinking water. For mice, there were 8 studies in 3 strains, including 2 inhalation studies and 6 drinking water studies. This overview slide displays all animal studies. We group studies by species, route of exposure, strain and sex, and administered doses. All reported studies are long-term bioassays. In rats, 10 studies, highlighted in red font, has examined postnatal exposure to vinyl acetate starting at 6 weeks of age or later, with exposure duration of 100 or 104 weeks, as noted in M for male, F for female rats, and in parental or F0 rats in the 2 generation studies. For example, there are 2 inhalation studies in rats, 1 in males and the second in females. Additionally, 6 studies were focused on early life exposure, studying preconception and or in utero, continuing after birth to the offspring or F1 animals until 104 weeks of age. In mice, the studies in red color show 6 postnatal exposures with treatment durations of 78 or 104 weeks, and 2 studies were early life exposures in F1 animals, studying in utero and continuing after birth until 78 weeks of age. The bright blue represents studies with treatment-related or positive tumor findings. Specifically, positive findings were reported in 13 rat studies and 5 mouse studies. Now I will show studies conducted before and after the IARC 1995 monograph. studies outlined in blue boxes are the ones IARC relied on as the basis for the classification of vinyl acetate. There were 4 inhalation studies in rats and mice, and 4 drinking water studies in rats available at the time. Now, in the HID, OIHA incorporate additional studies published after the IR classification, showing in the red boxes. There are 16 drinking water studies, including 10 rat studies and 6 mouse studies. Among the positive studies added after 1995, many tumor sites identified are distant from the site of entry. In the following slides, I will take you through the findings from the rat and mouse studies. We have many tumor instance tables to present. In the following slides, each tumor instance table is organized by tumor site and type, administered concentrations, and exact trend test values. Tumor instance with asterisk mark in the treated group indicates that there is a statistically significant increase compared to the control group by pairwise comparison. I will refer to these findings as significant increase, and I will refer to a statistically significant dose-related trend when p-value is less than 0.05 as a dose-related trend. In addition, rare tumors are illustrated with R in all slides. Now I will present you tumor findings from rat studies. In the 104-week inhalation studies of Sprague Dawley or SD-derived CRL, CD, SD, BR rats, animals were exposed to vinyl acetate by inhalation starting at 6 weeks of age for 104 weeks. In male rats, nasal tumors, including nasal squamous cell papilloma, squamous cell carcinomas, and carcinoma in situ were observed. Total nasal tumors were significantly increased in the high-dose group with a dose-related trend. Exact trend test values are presented in the last column on the right. Spontaneous occurrence of nasal tumors is rare in male rats, so each type is labeled with R. In the corresponding inhalation study conducted in female rats, rare squamous cell carcinomas of the nasal cavity were observed in the high-dose group, but not in the control animals. This table is the Fisher 344 rat studies. Animals were treated with vinyl acetate starting at 7 to 8 weeks of age in drinking water for 100 weeks and observed up to additional 30 weeks. Females, as shown here, instances of liver hepatocellular adenomas, uterine endometrial stromal polyps, and thyroid C-cell adenomas were significantly increased in the high-dose group. Those related trends were observed for uterine, thyroid, and pituitary tumors. In the corresponding study conducted in males, no treatment-related tumor findings were observed. In the studies of Fisher 344 DUCRJ rats, animals were administered vinyl acetate in drinking water starting at 6 weeks of age for 104 weeks. In male rats, tumors were observed in the oral cavity and testis. In the oral cavity and lip mucosa, squamous cell carcinomas and squamous cell papilloma and carcinoma combined were significantly increased in the high-dose group. Testis, interstitial cell tumors were observed with a dose-related trend. In the corresponding study in females, tumors were observed in the oral cavity, thyroid glands, and mammary glands. The oral cavity squamous cell carcinomas were increased with a dose-related trend. In thyroid glands, significant increases in B-cell adenomas and adenoma and carcinoma combined were observed in the mid-dose group. Now, I will present you the 2-generation studies in Sprague Dawley or SD rats in 2 slides. Here, male and female parental or F0 rats were treated with vinyl acetate in drinking water starting from 17 weeks of age and continuing for 104 weeks. The offspring or F1 rats were exposed to vinyl acetate starting in utero through lactation, then post-weaning in drinking water until 104 weeks of age. This slide presents findings for the male rat studies. F0 animals, pancreatic islet cell adenomas were significantly increased at a high dose with a dose-related trend. In F1 animals, squamous cell carcinomas of the oral cavity and lips were significantly increased in the high-dose group. For stomach, squamous cell carcinomas were significantly increased in both dose groups with a dose-related trend. Additionally, rare pancreatic exocrine adenomas were significantly increased in the low-dose group. This slide presents tumor findings from the female SD rat studies. F0 animals, for stomach squamous cell carcinomas were observed in the high-dose group. F1 females, squamous cell carcinomas of the oral cavity and lips and for stomach were significantly increased in the high-dose group with dose-related trends. And adrenal gland pheochromoblastoma were significantly increased in the low-dose group. In addition, rare tongue tumors were observed in the high dose. The next 3 slides are the 2-generation studies in Wistar rats. Male and female F0 rats were administered vinyl acetate in drinking water starting from 17 weeks of age and continuing for 104 weeks. F1 rats were exposed to vinyl acetate starting in utero through lactation and then post-weaning in drinking water until 104 weeks of age. This slide presents tumor findings from the male rat studies. F0 animals, no treatment-related tumors were observed. F1 animals are showing in the table squamous cell carcinomas of the oral cavity and lips were significantly increased in the high-dose group with a dose-related trend. Tumors of the pharynx, esophagus, forestomach were observed in the high-dose group. Incidences of pancreatic exocrine adenomas were significantly increased in the low-dose group. In adrenal glands, pheochromoblastoma were significantly increased in the high-dose group with a dose-related trend. This slide presents findings from the F0 female Wistar rat study. There was a dose-related trend in lymphomas and leukemia of the hemolympho-reticular tissues. Adrenal gland pheochromocytomas were significantly increased in the low-dose group. Uterine fibrosarcomas were observed in the high-dose group. In F1 females, tumors were observed in multiple sites. Tumors of hemolympho-reticular tissues were significantly increased at the high dose with a dose-related trend. Squamous cell carcinomas were observed in several tissues. The The oral cavity and lips, the incidence was significantly increased at the high dose with a dose-related trend. Tongue, there was a significant increase at the high dose. Esophagus, a dose-related trend was observed. For stomach, tumors were observed at the high dose. Additionally, uterine adenocarcinomas were significantly increased at the high dose with the dose-related trend. Slide summarizes the drinking water studies in male and female CRL-CD SDBR rats. Animals were exposed to vinyl acetate throughout all life stages, studying preconception and in utero parental animals, and continuing after birth. F1 animals were terminated at 104 weeks of age for examinations. Males, 2 squamous cell carcinomas of the oral cavity were observed in the high-dose group. Females, no treatment-related tumors were observed. These are all the rat tumor findings. Now I will present you tumor findings in mouse studies. BRJ-BDF1 mouse studies. Animals was treated with vinyl acetate in drinking water starting at 6 weeks of age for 104 weeks. Male mice, as shown in the table, in the oral cavity and forestomach, there were significant increases in squamous cell carcinomas and papilloma and carcinoma combined. In esophagus, significant increases in squamous cell carcinomas were observed in the high-dose group. In addition, rare larynx tumors were observed in the high dose. The corresponding studies in female mice, squamous cell carcinomas, papilloma and carcinoma combined of the oral cavity was significantly increased in the high-dose group. Squamous cell papilloma and carcinomas of the forestomach were observed in the high-dose group. Additionally, significant increases in spleen malignant lymphomas were observed in the low-dose group. Now I will present the 2-generation studies in Swiss mice in 3 slides. F0 animals were treated with vinyl acetate in drinking water starting at 17 weeks of age for 78 weeks. F1 animals were exposed to vinyl acetate starting in utero through lactation and post-weaning in drinking water until 78 weeks of age. F0 males, no treatment-related tumors were observed. F1 males, as shown in the table here, tumors were observed in organs of the digestive system, including oral cavity, tongue, esophagus, and forestomach. Significant increases in squamous cell carcinomas of the oral cavity and esophagus were observed in the high-dose group. Forestomach, the carcinomas were also significantly increased in the high-dose group with a dose-related trend. Continue to the tumor findings in female Swiss mice. F0 animals, as shown in this table, squamous cell carcinomas of the esophagus and acanthomas of forestomach were significantly increased in high-dose group. F1 females, tumors were observed in tissues of the digestive system, in the uterus, lungs, mammary glands, and Zimbel glands. Squamous cell carcinomas of the oral cavity, tongue, esophagus, and forestomach were significantly increased in the high-dose group. Forestomach, Acanthomas were also significantly increased in the high dose group. And simple gland carcinomas were observed with a dose-related trend. Completes the reporting of tumor findings for mouse studies. Here we summarize all animal tumor findings associated with vinyl acetate treatments, organized by species and strain. The first column on the left is the organ system, and then the tumor site. This arrangement makes it easier to compare tumor site similarities across different strains and species. Each row, M is for male and F is for female, and rare tumors are noted as superscript R. Bold font for male or female indicates tumors with a significant increase, as determined by pairwise comparison and or a significant trend. Tumors not in bold include those with a significant trend driven solely by increases observed at the high dose or the occurrence of rare tumors. Oh, okay. Okay, great. Yeah. Just a reminder that the tumor findings in SD-derived rats were from inhalation studies, as outlined in the blue box. And findings in all other strains were from drinking water studies.
Excuse me, Kate, the display is cutting off one of the rows at the bottom of the slide.
Right. You can see the. Oh,
And
So committee members, can you see the bottom row of the table showing immune systems? No? Okay. So just so for information, the bottom row is cut off and it shows immune system. The tumor sites are hemolympho-reticular tissues, and their findings for female rats, investor rats, and also female CRJ-BDF1 mice.
yeah, it's both are in drinking water studies. So as shown here, in the respiratory system, nasal tumors were reported in both male and female CRL, CD, SDBR rats. There was a significant increase in males, and there was only a dose-related trend in females. So the female is not bold. The tumors in both male and female are rare, as marked with superscript R. Moving down, in the digestive system, oral cavity tumors were observed in both males and females, and across 3 rat strains and 2 mouse strains. You can also see that tumors were observed in the endocrine system, the reproductive system, and in auditory and immune system, and Dr. Saunders mentioned. I want to list each tumor site here. So here, highlighted in the red color, are tumors observed in organ and sites distant from the site of entry, including lung, liver, pancreas, endocrine, reproductive, and hemolympho-reticular tumors, which cut off from the current slideshow, from drinking water studies, all from drinking water studies. In summary, vinyl acetate induced tumor-related tumors in multiple organ systems in both rats and mouse. Some tumor types were observed in multiple strains and in both sexes. In addition, among the tumors reported, several are rare tumors. This concludes the reporting of animal carcinogenicity evidence. Now I will turn it over to Dr. Ricker to continue.
Now switching to, so can you hear me now? Better? I'm eating it. Okay, so we're now switching to the pharmacokinetics and metabolism of vinyl acetate, and I start with a brief overview. So following inhalation, vinyl acetate is quickly absorbed and distributed throughout the body, and it is largely excreted within 24 hours, with the majority excreted in expired air and small amounts in urine and feces. And the excretion products include carbon dioxide and acetaldehyde. The metabolism of vinyl acetate proceeds primarily via two key enzymes. The first enzyme is a carboxyl esterase, and it metabolizes vinyl acetate to acetic acid and vinyl alcohol. Vinyl alcohol is unstable and quickly rearranges to acetaldehyde, a known carcinogen. In a second step, acetaldehyde is also metabolized to acetic acid via aldehyde dehydrogenase, primarily the aldehyde dehydrogenase 2, ALDH2 for short. And the resulting acetic acid of either reaction is then introduced into the tricarboxylic acid or Krebs cycle, where it is further metabolized. There are other metabolic reactions happening as well, and we look at these in more detail on the next slide. So here's the metabolism of vinyl acetate. Vinyl acetate is shown here in red on the middle left side. And we start with a minor pathway whereby vinyl acetate is conjugated with glutathione. Moving on to the major metabolic pathway. In the main pathway, vinyl acetate is oxidized to acetic acid, and vinyl alcohol via carboxyl esterase, or CES for short, shown here. And vinyl alcohol, as I mentioned, is unstable and quickly rearranges into acetaldehyde, which is a known carcinogen. In turn, acetaldehyde is further metabolized by ALDH2 to another molecule of acetic acid, and as I mentioned, introduced into the Krebs cycle via acetyl-CoA synthase. The oxidation of acetaldehyde to acetic acid is mainly carried out by the ALDH2 and to a lesser extent by ALDH1. So ALDH2 is a key player in the detoxification of acetaldehyde, and we will hear more about this polymorphic enzyme shortly. Continuing with metabolic reactions, downstream of acetaldehyde, DNA adducts and DNA protein crosslinks can be formed, and these have been observed in rodents, in vivo and in vitro, following vinyl acetate or acetaldehyde treatments. Acetaldehyde can also be oxidized by two additional enzymes. These are the aldehyde oxidase and xanthine oxidase, and both enzymatic reactions can form reactive oxygen species, ROS for short, and the xanthine oxidase also produces alkyl radicals, and these radicals can lead to alkylated protein adducts. As I briefly mentioned, ALDH2 is a polymorphic enzyme in humans. So a single nucleotide polymorphism in the gene, known as RS671, encodes a non-functional protein, and the resulting variant allele is denoted as ALDH2-STAR2. Individuals that are homozygous wild type have full ALDH2 activity. Individuals that are heterozygous have less than half activity, as the polymorphic allele is dominant negative, and individuals that are homozygous for the polymorphism have no activity. So with ethanol consumption, accumulation of acetaldehyde leads to various symptoms such as facial flushing and is commonly referred to as alcohol flushing syndrome. The ALDH2-STAR2 polymorphism is mainly found in people of East Asian descent,
up to 40% of Chinese, Korean, or Japanese individuals are heterozygous, and another 5 to 10% are homozygous for the polymorphism. This polymorphism has also been reported in some Southeast Asian population at lower frequencies, and it is not found in other ethnic groups. In conclusion, a reduced capacity to metabolize acetaldehyde can lead to buildup of this metabolite, and based on census data, OEHA estimates that this polymorphism could affect at least 1 million people in California. So to summarize the key points for the metabolism, vinyl acetate metabolism generates acetaldehyde, and the balance between metabolic activation of vinyl acetate via the carboxyl esterase and clearance of acetaldehyde by ALDH2 largely determines the overall level of acetaldehyde in the cell or tissue, with aldehyde dehydrogenase 2 playing a critical role as the detoxifying agent. The rapid generation of acetaldehyde coupled with slow clearance can lead to increased levels of acetaldehyde following vinyl acetate exposure. The situation arises in individuals who are heterozygous or homozygous for the RS671 polymorphism, and in turn, unmetabolized acetaldehyde can then form DNA adducts, DNA protein crosslinks, reactive oxygen species, and alkylated protein adducts. This concludes the metabolism section, and I'm now turning the presentation over to Dr. Cheng, who will present the key characteristics for vinyl acetate.
Thank you, Dr. Ricker. We organized the mechanistic data for vinyl acetate by the 10 key characteristics of our carcinogens, or KCs, that are used by IARC and NCP in their evaluations of carcinogenicity evidence. The key characteristics were identified by IARC based on a comprehensive review of mechanistic information for known human carcinogens in IARC Group 1. As detailed in the HID, there is evidence on vinyl acetate for 3 of the 10 KCs. Data from humans and animals in vivo, animals and human cells in vitro, and acellular systems were identified for some of these KCs. A brief overview of each will be presented. On the bottom left-hand side of each slide, there is a reference to the section in the HID for each KC. Starting with KC1 is electrophilic or can be metabolically activated. In rats exposed to carbon-13 labeled vinyl acetate in vivo, the labeled N2-ethyl deoxyguanosine DNA adduct was found in nasal respiratory and olfactory epithelia, as well as in peripheral blood mononuclear cells. As previously mentioned, acetaldehyde is a metabolite of vinyl acetate. Acetaldehyde has been shown to bind directly to DNA and can form DNA adducts such as N2-ethyl 2'-deoxyguanosine, 1,N2-propanodeoxyguanosine, and N2-ethano 2'-deoxyguanosine. Next, KC2 is genotoxic. Some of the effects presented here were observed with non-cytotoxic concentrations of vinyl acetate. For detailed information, please see tables 29 and 30 of the HID. A number of studies have reported increased chromosomal effects with vinyl acetate. One human observational study observed increased chromosomal aberrations in lymphocytes of polyvinyl acetate manufacturing workers. Several studies in both animals and human cells in vitro have reported increases in micronuclei, chromosomal aberrations, and sister chromatid exchanges following vinyl acetate treatment. Sister chromatid exchanges were also observed in animal studies in vitro after vinyl acetate exposure. There are also some data on vinyl acetate-induced DNA damage. Vinyl acetate exposure induced DNA adduct formation in the nasal epithelial and peripheral blood mononuclear cells in vivo animal studies. DNA crosslinks were observed in human leukocytes exposed to vinyl acetate in vitro. DNA protein crosslinks were observed in rat nasal epithelial cells in vitro and an acellular system using plasmid DNA and calf thymus histones incubated with rat liver microsomes. Continuing with evidence of mutations, vinyl acetate induced mutations in human TK6 lymphoblastoid cells in vitro and mouse lymphoma cells incubated with or without S9 fraction in vitro at the thymidine kinase locus. No effects were observed at the HPRT locus in human cells. In contrast, no mutagenic activity of vinyl acetate was observed in tests conducted in bacterial strains. Lastly, there was some data for KC10, alters cell proliferation, cell death, or nutrient supply. The data below are all from rodent studies in vivo. These findings were observed alongside neoplastic findings from the 2-year carcinogenicity studies that were previously presented by Dr. Lee. Increased cell proliferation was observed in male rats in the nasal cavity epithelium, nasal olfactory epithelium, and oral cavity maxillary mucosa. In male mice, increased cell proliferation was observed in basal cells of the mandibular oral cavity mucosa. Studies in rats and mice have reported vinyl acetate-induced hyperplasia in multiple organs. Basal cell hyperplasia of the nose was observed in male and female rats. Thyroid gland C-cell hyperplasia and hyperplasia of the esophagus and stomach were observed in female rats. In both male and female mice, hyperplasia was observed in the tracheal epithelium, submucosal gland, oral cavity, and esophagus. Dysplasia is characterized as a disordered growth and abnormal proliferation and is more advanced than hyperplasia. Dysplasia was also observed in animals exposed to vinyl acetate. Squamous cell dysplasia of the esophagus was observed in male and female mice, while female offspring of those exposed mice had dysplasia present in the tongue, esophagus, and zimbal gland. I will now briefly highlight shared tumor findings and genotoxic effects between vinyl acetate and its key metabolite acetaldehyde. I will start with shared tumor findings, or tumor sites. From inhalation studies, nasal tumors were observed in rats exposed to both chemicals. Laryngeal tumors were observed in rats exposed to vinyl acetate, while these types of tumors were observed in hamsters exposed to acetaldehyde. From drinking water studies, hemolymphocytic, pancreatic, and mammary gland tumors were found in rats exposed to either vinyl acetate or acetaldehyde. Most tumor sites from acetaldehyde exposure overlapped with the tumor sites induced by vinyl acetate. However, vinyl acetate exposure targeted several other sites and organs in the respiratory, digestive, and endocrine systems. Vinyl acetate and acetaldehyde also have some shared genotoxic effects. First, both vinyl acetate and acetaldehyde produce micronuclei, chromosomal aberrations, and sister chromatid exchanges in rodents in vivo and human and rodent cells in vitro. Second, both chemicals produce the same type of DNA adduct and form DNA crosslinks. Third, both induce mutations at the thymidine kinase loci in humans and mouse cells in vitro. That concludes our presentation for today, and thank you for your attention.
Very good. Thanks to all the staff members for that very helpful summary of the evidence. At this point, we have an opportunity for the members of the committee to ask questions of clarification. And I'm going to take the chair's prerogative and begin by asking a couple of questions. So we heard about the metabolism of vinyl acetate to acetaldehyde. I have a question about and how that metabolism of acetaldehyde by ALDH2 varies according to the polymorphism of that enzyme. How much variation is there in the metabolism of vinyl acetate to acetaldehyde by carboxyl esterase? Do we have any information about that?
We had, we had no specific information on carboxyl esterases. There seemed to be some indication that some may be causing more activation of vinyl acetate, but I think others did not confirm this, so it's unclear, and it's also unclear which carboxyl esterase exactly metabolizes the vinyl acetate. It's either CS1 or 2, but we did not find a clear evidence for either enzyme.
Thank you. One other question really quickly. describe the, going back to your description of the metabolism of vinyl acetate or, sorry, acetaldehyde to its byproducts. How much of that evidence comes from studies of exposed humans?
Are you referring to DNA adducts and reactive oxygen? I think, double check, but I think it's primarily animal studies, but some products were found in vivo.
Okay, thanks. At this point, we'll go around the committee and see if there are other questions. This configuration with all of us lined up in a row is a bit awkward, so I may not see you if you want to speak, but it looks like Dr. Eastman is making motions there. We'll begin with you, Dave.
Thank you. And thank you for a very nice presentation. Pretty comprehensive in some aspects as well. I do have a few questions. I guess the first one relates to the genotoxicity. One of the things that's intriguing for me is that, so vinyl acetate was induced micronuclei when administered by IP injection. But it seemed like when administered by other routes, primarily oral routes of exposure, you didn't see any micronuclei. Any particular insights as to why that might be the case?
Looking at the data, I think even for IP injection, there's a negative study, so I'm not sure if there's a route specificity there. But the database is limited. There are not too many studies of micronuclei in animals.
I think there were like 3 negatives or something like that. It was enough. I mean, obviously the data and the mechanisms, there's quite a bit of evidence that it's genotoxic in vitro and it makes sense. But I was just curious about that. Another point that was raised was, just for my information, and this is one of the public comments, was they made an issue about the increase in tumors that we're seeing were primarily at site of exposure or site of contact. Does that make any difference in sort of the way you assess the risks?
We actually have a backup slide to show you whether which tumors were induced at sites distant from the site of entry. So I'd like to ask Kiana to share backup slides.
No, they presented it, so okay. I mean, I'm just curious. That was made as an issue, but when you essentially doesn't have to be vinyl acetate, any chemical. Do you make a distinction when you're doing the risk assessment, whether it's at site of exposure or a distal site?
I would say not at the step of the hazard identification step.
Okay, all right. That's helpful. I had one other that's kind of specific, but one of the other public commenters, and maybe that will come up, had comments about sort of study quality, and a lot of these are older studies. But one in particular, they made some comments about the Ramazzini Institute. And it was my understanding that the questions with the Ramazzini Institute were primarily on lymphohematopoietic tumors, and that was pretty well limited. And the other ones seemed to be fine. It was just the interpretation. Does that seem to impact, because these seem to be done during that time frame? Was that taken into consideration when you reviewed things?
Yeah, we also have a backup slide if you have the time to look at it. But yeah, we consider NTP and US EPA's review and pathology working group review of the Ramazzini studies. So among the tumors as you've seen today, yeah, there is the hematolympho-reticular tissue tumors in rats from the Ramazzini studies. You could, make your own judgment on it. But yeah, US EPA continue to consider solid tumor findings from Ramazzini Institute to be valuable and reliable. But yeah, they do consider the lymphoma and leukemias of the respiratory tract to be unreliable. Based on the limited number of studies they review, they did not review the study for vinyl acetate, but yeah, the study for vinyl acetate was conducted during the same time period at the Ramazzini Institute.
Okay, thank you. I understand they've worked out with NTP's pathologists, and they're now pretty consistent, but that was during a period of time there was some difference in gradation. Anyway, and I think, oh, one last thing is for the epidemiology on this recent study from 2024, which was the vinyl acetate exposures in Southern California. Do we have an idea what were the sources were for that vinyl acetate? This was a ecological study, looked at what would be the origins of that vinyl acetate. I mean, if you don't know it, you don't, doesn't matter, but I was curious.
I don't think it's stated in the paper where the exposure is coming from, but yeah.
Okay, well, thank you.
We would just assume it's industrial.
Yeah, if I may comment on that, and they do say in the paper that it's industrial sources and water contamination. That's what they presume.
I think it's just measured in air, and the point sources are not specifically. Dr. Eastman, if you're finished, I think what we'll do to make it easier on
I'm
me.
done, thanks.
You're not.
Oh, I'm done, thanks.
Okay. Make it easier on me. I think we'll just go with the committee members on my left. The audience is right first, so I'm going to look down there and see if anybody else wants to ask a question.
I wanted to follow up on the epidemiologic study. Can you comment on, I mean, none of these exposures happen in isolation. So can you comment on the Heck et al. Study regarding the correlation with other exposures and how, or any data they provided on sensitivity and specificity of that exposure?
Yeah, they did look at that. They did look at the correlations, and they found that vinyl acetate wasn't highly correlated with any of the other measured air toxics. The R-squared ranged from 0.03 to 0.35, and that was with methyl isobutyl ketone, the higher one. So they did look at that. Yeah.
Others this way, Jason?
Thank you. Just follow up on Dr. Loomis's comment regarding the ALDH polymorphisms. Maybe in future HIDs, it would be helpful for the committee if there is known information on homologous enzymes in the animal models to know whether there is a polymorphism there as well. I mean, generally the animal models are going to be outcrossed and backcrossed to ensure that they are, effectively wild type. But there might be something there that would give some further insight into some of this, the metabolic side of things. So maybe there is information, maybe it isn't known, but if there is, it would be helpful, I think, if there's something to correlate there.
We didn't have those specific data, but we include data on knockout mice that are in the HID.
Okay. Thank you.
What else on that side? Go.
Very much enjoyed your summarizing this plethora of data. I mean, it's a lot of data. So a lot of animal studies done, mouse and rat, a lot of animal carcinogenicity studies data. And many of them are dose dependent and many have trend effects as well. So my occurrence in reading this large summary of data is that there is a large positivity of information on this compound. Am I missing something, or is that the way you see it too? I mean, I'm not seeing zeros most of the time. I'm seeing positive studies. So does your team feel that that is a correct interpretation of this data?
So I'll take a stab at that, Dr. Landoff. We have presented quite a bit of data. You've seen many tables from the animal studies of tumor incidences, but we will remind you that your committee is the state's qualified experts to make the final judgment. So
Well, that's true, but I'm asking it since you've lived with the data longer than we have.
I think you're putting them on the spot a little bit.
I'm sorry, I couldn't hear your comments down there.
They seem to be feeling like you're putting them on the spot a bit here.
Well, I am, but not in a bad way. I'm just saying you reviewed a lot of the data and I think I see a lot of positivity in it. And I was asking if that's what you saw since you've lived with it so long.
I think we have seen quite a
Okay,
bit.
that's all. It's not a trick question. That's all I wanted to know. And thank you very much.
Okay, Dr. Crespi.
Yeah, I had a question about a detail from the Heck paper that I didn't see, and I wondered if maybe the staff had seen it. And that is the hazard ratios were for a 1 interquartile range increase in exposure. And it wasn't clear to me whether they were using the same interquartile range for all of their analyses, or if that interquartile range was specific to each, to the analysis sample in their various analyses. So I didn't see that in the paper, whether they were specific about that. So I just wondered whether you had seen that or might have insights.
Hi, my name is Neela Guha. I'm a staff scientist with OEHA. I'm looking at the Heck paper currently under the methods section, and this is what they say about the interquartile range. We employed Cox proportional hazard models to assess time-dependent air toxic exposures and evaluated its effects on breast cancer risk per interquartile increase. So looking at that, it looks chemical specific for each interquartile increase, but that interpretation would be up to you.
Yeah, I assumed it would be chemical specific. I just wondered whether it was specific to the sample being analyzed in each of their models. I don't think it's specified in the paper, so I just wondered whether you might have seen that.
I'll
or
keep
had
looking in the
insights.
paper, but I haven't seen anything.
Yeah, thanks.
Yeah, I had a similar question about that paper. Those odds ratios are rather high for an environmental study, and I find them hard to interpret without knowing what the zero exposure level would be. Now, going to my right, yep, first question.
Hi there. Thank you for the presentation. Excuse me, I'll have some procedural questions because it's my first meeting. One of the things was said here was that we need to use generally accepted approaches. Some of the studies we're reviewing are 30, 40 years old. Do we consider generally accepted approaches at the time of the study or generally accepted approaches at this moment?
I would say a well-conducted animal carcinogenicity study, how you judge that have not changed too much over the years. So if you have any specific question to study design for some of the older studies, you could let us know and we could try to comment on them.
Okay, so we assume current standards, right? That there is not, okay. And I'll go with that in a second. The other thing I wanted to ask is, when you're selecting the literature that you're reviewing, presumably you use predominantly peer review literature. And the reason I'm asking, I was looking at the Russian article specifically. Is there, and there are other articles in Russian that report that, but you have selected that presumably because it was reviewed in an American journal. Is that the case? Or do you have any specific, for foreign literature, do you have any specific set of criteria to search for them?
I don't think we select the language limitation when we're searching for articles, but we are looking at peer-reviewed articles.
Which are indexed by PubMed, right?
PubMed and some other is detailed in our document.
So my question there was one of the, well, there's a lot of tables when we're talking about the mouse studies, and there have been a lot of statistical tests that have been done. And I was just wondering, if one assumes that these studies are independent, shouldn't these p-values be corrected for multiple hypothesis testing?
This is Martha, Sandy, the animal bioassays, that the way they're analyzed by the National Toxicology Program and IARC and other authoritative bodies, it's the concept is you're exposing animals and testing to see if there's an increase in tumors, and it's there are no corrections that are typically made. It's generally accepted that that's not the practice for analyzing bioassays data in general.
But you mean that within a study?
Within a study.
What about
yes.
across the studies?
We each study is different, and even the same strain of animal, the study conducted in a different laboratory, the conditions are different. So we're looking at increases in the treated versus the control, the concurrent control. And we do not do corrections across studies that may have been conducted at different points in time in different laboratories.
Okay, okay. So the other question I have was about the because a lot of this relies on pathology, the mouse work, right? Somebody has gone and visually reviewed the actual slides. For these studies, do you know how many pathologists have reviewed each one of the mouse tumors to determine whether they are invasive or whether they are adenomas?
Well, these studies were conducted in different institutes, right? Some are in Italy, some are in Japan, some in the US. So each study's protocol may be different, and we try to provide that information if additional pathology review was provided other than the publication. So the situation could be different for each study.
I understand. And when I was looking at the papers, there wasn't that comes to mind the generally accepted standards now versus before, because most of those papers, at least when I was looking at them, they did not provide that information. And what I do worry, especially when it comes to the invasive, because they will report a lot of premalignancies, a lot of adenomas. And there is huge amount of disagreement when you have esophageal squamous dysplasia, especially a high-grade dysplasia, and esophageal squamous cell carcinoma. You'll get 5 pathologists to review it. 3 will say it's dysplasia, 2 will say it's squamous cell, invasive one. That's why I was wondering whether there is any specific standard that was used. Let me see. I suppose the last question I have was about the AP study, the Hecatol study. And the question there was, you showed that there was correction for smoking. Was there correction for alcohol consumption? I don't think there was, but
Yeah, all models were adjusted for a whole bunch of confounders. One of them is alcohol use, non-drinker versus drinker.
Okay.
Yeah.
Okay, thank you.
Hila, did you have something to add to that?
In addition to alcohol use, those models were adjusted for risk factors for breast cancer, the typical risk factors, known risk factors for breast cancer.
Okay, continuing on this side.
I don't have any questions of clarification for the staff.
Dr. Stern, questions?
I just have a very quick question, which is more about notation. So I was interested in, when I look at the animal experiments, I was interested in looking at the data for mammary gland because of the HEC study. So you had it on your slide 20, the my understanding is that the notation you're using is that the trend is significant because the p-value is less than 0.05, but the actual number of tumors observed at the high dose compared to the control is not significant, and that's why you didn't put an asterisk. Is that my understanding correct? So significant trend, but not significant pairwise comparison. Okay,
That's correct.
good. I just wanted to understand that.
Okay, thanks. Now we'll go to the two members joining online. Dr. Besaratinia, questions? Can't hear you. You're on mute.
Yes, thank you very much. Can you hear me?
Now we can.
Okay, thank you. First of all, thank you, the staff, for this report. It was quite informative. I have a few questions. Firstly, with regard to the human study, the single human study, which was also showcased this morning. Understand that the exposure assessment was done using the geocoding data and residential history in order to evaluate the neighborhood air pollution level. And this was done with a 5-year lag time. Considering that early life exposure to endocrine disruptor and mammary gland carcinogen is known to result in breast cancer later in life. Would you comment on that aspect?
Yeah, that is a weakness of the studies, that they only looked at it in that specific period and did not account for early life exposures. But that's what they have.
Okay. And the second thing is that if I got it correctly, they exclusively looked at invasive breast cancer. Am I right on that?
Yes, and they excluded ductal carcinoma in situ, I think.
Yeah, and actually, I want to underscore that fact because DCIS, a quite significant portion of breast cancer cases are DCIS, up to 40 to 45% of DCIS advance to invasive breast cancer. And would you consider this also a major drawback of this study, that all the DCIS cases were excluded from this study?
Yeah, they could be missing some cases there. Yeah.
Correct. And then with regard to, thank you for your response on the human studies. I also wanted to see whether there is any additional information with regard to the metabolic pathway of vinyl acetate, since we have put so much emphasis on the key metabolite of this compound, acetaldehyde. I'm wondering, is it known what portion of the vinyl acetate that is taken up by the cells, either in vitro or in vivo experiments, is converted to acetaldehyde and subsequently results in DNA adduct formation or DNA protein crosslinks or reactive oxygen species, versus the fraction that is detoxified, for example, by conjugating to reduced glutathione GSH?
I think the glutathione conjugation, very little is known, and we just had data from some animal studies where they showed a decrease in the GSH pool. So we don't have any quantitative data on that.
So proportionally, we don't know whether the majority of the vinyl acetate is going to turn into acetaldehyde or DNA or protein reactive agent, or it can simply be detoxified and eliminated.
Well,
is that what you're saying?
Well, I said it depends on your, the overall amount of vinyl acetate and also your endogenous levels of acetaldehyde and the functioning of your ALDH2, how well
Okay.
that's tuned to detoxify. And
Okay.
we have studies in animals that show if you have a knockout gene, or we have studies in some human cells that show that acetaldehyde levels can increase significantly if the ALDH2 is non-functioning.
If I may jump in.
Sure.
So in the KC1 and KC2 section of the HID, we do introduce when a study tests animals or cells with both vinyl acetate and acetaldehyde. And in KC1, there are 2 studies in animals in vivo where DNA adducts were seen as low as 10 parts per million of vinyl acetate. They also treated animals with acetaldehyde. So if you want detailed information, quantitatively speaking, you can look at the papers.
Okay.
The proportions may be different depending on the study design and study conditions. But in KC2, we also introduced whenever vinyl acetate and acetaldehyde were both treated, both used, so you can compare.
Okay. Thank you for that note. My last question is with regard to the animal studies. Could you please put in context these doses that were tested in different animal models and kind of let us know how they compare to doses to which humans are exposed on a daily basis, particularly when we are talking about inhalation experiment. I know earlier we indicated that we are not particularly interested in the dose, but I just wonder if this information is available to be presented to the committee at this moment or not.
I will let the scientists answer the question to the extent they can, but just again, yes,
Yeah.
as far as not being as interested in it, just as a
Yeah.
reminder, it's hazard identification. Thank you.
Yeah.
As we look at the exposure section, of the document, we have discussed that probably the most exposed folks are in the occupational setting. And I don't think we have any recent information on what those levels might be in the workplace.
Okay, thank you. That's all I have for now.
Okay, thank you. And let's go over to Dr. Belcher.
Thank you. Can you hear me?
Yes.
Fantastic. Yeah, I have a variety of questions and a couple of details probably I could clarify. First, I think I want to compliment the scientists in the group. I read a lot of reports like this. It was coherent, organized, very easy to read, and unusually concise for the amount of information. So I found it a pleasure to read this report. So thank you. I think the ALDH2 is really important. You recognize it being important. You mentioned it throughout the report. There are a few things I think that should be asked to clarify. One important thing is because we know this is the enzyme that detoxifies perhaps really the most important metabolite, the acetaldehyde. Really, a question I have for you is, to what extent did you look to see the spectrum of tumors observed in people mutant for this gene are the spectrum of tumors that we've seen associated with vinyl acetate?
Unfortunately, we don't have any direct evidence regarding vinyl acetate exposure in conjunction with this polymorphism of ALDH2 and tumors.
Well, that was my third question I was going to ask you. My first question is, if you just look at the tumors you saw in rats and mice, to what extent is that phenocopy the tumors you see, say, in the mice that are knocked out. We all know, you know that I've worked in animal models for decades. I know you know that they're models. We know humans have been studied for years with this mutation. I've been to conferences just on ALDH2. There was one hosted at Stanford that I spoke at just a few years ago. To what extent does it map? You might predict that if vinyl acetate's a carcinogen, you would expect to see almost the same spectrum of tumors you see in humans who have this mutation or in mice who have this mutation. I'm just asking you, did you look?
I don't think we have that information at hand, no. And I think we have to consider route of exposure and the metabolism, intracellular metabolism for each chemical that might be metabolized to acetaldehyde.
That's a fair point. The other thing I wondered is there is a reported increased risk of breast cancer in humans who have a mutation of ALDH2. It's not as great as a relative risk as what Keck reported. Probably that would be the same answer. It's not really an equivalence.
Yeah, in the HID, we do have a paragraph talking about this polymorphism and people's risk of cancer. But again, we don't have any data with vinyl acetate exposure in humans and this polymorphism and risk of cancer.
We do know, though, that the ALDH2 mutant is much more common amongst these Asians. You highlighted that. In the study, in the Keck study, was there any effort to look to see if people of East Asian descent had a higher relative risk? I mean, the only thing I could see is they looked at Japanese Americans.
Yeah, and I think the paper said they attributed it more to like higher exposures based on where you might live than you know, the actual like differences in genetic susceptibility.
For the human studies, we talked about the lag time being 5 years. It is confusing to me they chose that. Lag time also allows you to look at latency. What was the duration range they felt people were exposed? I found it confusing reading the Keck study to know what they thought the mean duration of exposure they thought was.
Yeah, I'm looking through the method section of the paper again, and just the years of the NADA models that were taken. Geocoded addresses for 1998 to 2000 and 2001 to 2003 were then linked to the 1999 and 2002 NADA models, according to the 2000 census tracts. So that's the information we have on that.
The thing is, we'd like to have an idea what they thought for this population. What was the range of which they were exposed to air that had chemicals in it, to know whether or not there was a sufficient time for latency from exposure to having the disease cancer they use as a endpoint.
Yeah, I mean, you have the information of when the exposure was assessed and you know when the cancer time points occurred.
So I'm just asking, what's the time difference? How many years were they assuming it took for breast cancer to occur?
Can I provide a comment? Is that okay for me to comment on this at this point? So the way the study is done, as the team explained, is they geocoded their residential address with a 5-year lagging time, right, between the measure of exposure and the incidence of the case. They also know, they have information about residential history on these participants. So they were able to classify participants based on whether they had lived at that residential address for most of their time or as adults or not. And they did an analysis, a sensitivity analysis, stratifying participants based on whether they had moved or not, and they did not see differences. So they did take into account whether patients not patients, everyone had lived in that address for the 5 years only that they had considered or longer, or if they had moved earlier in their life and they didn't see that that had a difference.
Mariana, if I may say, I think what Dr. Felcher and both I were concerned were that we don't know how far back they went to assess exposure and see the duration of time these individuals who were diagnosed with breast cancer were exposed to that particular chemical. So that is quite vague. The description in the article doesn't really clarify it.
Yeah, my understanding is that they consider a minimum of 5 years.
Yeah, which would
So
be
that's the minimum time.
Yeah,
Which
It
is
could be
extremely
more.
short latency.
extremely short. For any type of cancer, that would be extremely short, as far as I know.
Yeah, but
Yeah.
in that case, you would expect that you would not see an association, right?
And if you do see, then you might think twice what this association is about.
I mean, it's possible that we're not talking about tumor initiation, we're talking about progression, and you're accelerating, like you brought up thoughtfully, DCIS, which is the precursor to anywhere from a quarter to 3/4, depending on which person's study you look at.
Yeah.
That's all we're trying to get at, is that there's a loose end in terms of it would have been nice to say, on average, this was what we thought people were exposed to polluted air to. The other aspect of this is that the NADA data has been used by lots of people, and I know it was brought up, I believe in the report, there's a Nyhoff study in 2019 that came to a different conclusion. It's also a very interesting paper using the data in a different way. And it seems like the main difference is the population was different. That this particular study, the Keck study, focused on a focused population in the LA. But I wondered if you thought about, because the Nyhoff study, I don't believe specifically focused on vinyl acetate. It focused on many other carcinogens.
So is this a clarifying question? I feel like we're drifting a bit into discussion of causal inference here, and
Sorry.
we don't need to go there just yet. Other people are eager to jump in, I can see, but maybe we should hold that discussion until later.
I apologize for making the discussion too broad. Those are the questions that I had.
Okay. Neela, did you have something to clarify there in response to those questions?
Yes, we just had an additional point of clarification again, looking at the paper. The exposure lagging was presented for 5 years only, but it was also conducted by 5, 10, and 15 years. And the exposure models were considered at the earliest time period that the NADA estimates were available.
But they indicated that the 10 and 15 years data were not sufficient for any type of analysis. That's why they excluded and exclusively used 5 years lag time.
That is correct. Those time periods had sparse data.
Yes.
Okay. Any other questions from you, Dr. Felcher? Are you finished?
One quick question about the animal studies. I wasn't clear. I think this is kind of asked, but I wasn't clear how they chose what doses to use. I have no problem with the doses. I just wasn't sure how was it clear there's some, because the dose range was chosen, was consistent amongst the different studies. Was there a reason?
Again, these studies were conducted by different institutes, but you can see studies of the Ramazzini Institute probably chose consistent dosing. They probably did previous short-term dose finding studies, but I can't comment on all of them. In the JBRC study, they typically include a short-term dose finding study as well.
Okay, let's do a quick survey of the committee and see if these discussions have brought up any other questions of clarifications, but not yet discussion on causal inference. Dr. Crespi, you got one.
I had a clarification or informational question. So in the HAC air pollution study, the cancer case ascertainment was from the California Cancer Registry, I believe. And is ductal carcinoma in situ, is that reportable to the California Cancer Registry or not?
Maybe while they're checking, we can see if there are any other questions on.
It should be reportable. It is, if it's cancer, is reported as localized.
Okay, so I was trying to determine whether it's reported and then the authors chose to not include it as a cancer outcome in this paper versus it wasn't available.
That's my understanding because based on my own experience working with the California Cancer Registry, localized cancers are reported.
Okay, thank you.
Okay, other questions on my left? Anything else? Doesn't look like it. On the other side? No? All right, I'm going to recommend that we break for lunch at this point. And when we do that, it's my duty to remind you that even during the lunch break, we're still governed by the Bagley-Keene Open Meetings Act. So you are not allowed to discuss the subject matter of the meeting among yourselves or to have phone calls, texts, or other electronic communications about that. You're also asked not to speak to third parties about the items under discussion, but if you do so, you'll be asked to disclose that and to describe the discussion that you had. So that can be part of the public record. So bottom line, best not to talk about it during lunch. Talk about sports or the weather or whatever you like. So with that, we will break for lunch for 45 minutes, and I think that means we come back at, let's say it's 12:40-ish, 12:40. Okay, that's when we'll come back.